It really is kind of more of the same stuff, so we'll see when we get into it. I'm going to give you a couple of definitions because it'll make more sense in a little bit.
Oh, Miss Belinda.
Yeah.
I have to leave early. I have a pal, but
Okay.
I have a website.
Okay, good.
And she's honestly right.
Almost were the exact same thing.
How's the situation with
That's what I said. I said, is that specs? I think I put no. He asked for it. Yeah. It's a little girly. It's a little. I think it's manly. I think it's manly. No, I think it's girly. Like it's up front.
Okay, so a sampling distribution is just a probability distribution like the ones we've been doing, like a normal distribution. But it's for when you've taken a bunch, we make our distribution based off of a bunch of samples of the same size. So if I was going to do a study, let's just say I was going to do a GPA study at Springtown High School, and so I came in and I took a sample of 50 students. And then I put all of the 50 students' name back in the hat, and I took another sample of 50 students. And then I put them all back in the hat, and I took another sample of 50 students. And I just did that multiple times. That would be where we would get a sampling distribution.
I have a real quick question for you.
Yeah.
Do you have a compass or a protractor?
I definitely have a protractor. I actually have. Are you trying to draw circles?
No, they want me to send it for my homebound kid.
I have. It's not a great one, but I have that.
Thank you.
Is it? What is it? Oh, yeah.
Oh.
There you go. I was gonna say, why is it like that? But yeah.
Apparently, I guess whatever program they have him in, he has to have it.
Yeah.
Draw stuff. So.
I may have a compass also.
I just haven't used an actual compass in years.
I mean, they're probably not great. But...
Oh,
Yeah, because they're
so
dangerous. That's
Yeah, y'all don't trust my kids
Yeah,
with
no.
the sharp
I'm not giving
points.
them that.
It would be 7 years.
That's funny.
No, y'all, I'm not gonna 7 years. Sorry, I made eye contact when I did that.
scared. I'm probably going to be going.
Thank you.
Yeah, no problem. Okay.
I'm gonna go till
So let's see. Sample distribution of a sample mean. So these things all have really big names, and so a lot of times I won't say the whole name because it's a whole lot to say. That's a mouthful. This is. This is a sampling distribution that is created from a sample mean. We're going to do one of these in just a minute, so you'll see what I mean by that. Okay, so standard error of the mean is a standard deviation, but they give it a different name because you'll see in just a minute, we make an adjustment because we get this distribution from so many different samples that we have to adjust our standard deviation. So they give it a new name and they call it standard error of the mean. This sampling distribution for means is another way of saying sampling distribution of a sample mean. It's just two ways of saying the same thing. People will say both, so it means the same thing. Then the last one, central limit theorem. This is a huge idea, and I've probably mentioned it a few times in passing. central limit theorem states that if your sample size is 30 or more, that your sampling distribution for sample means is going to be approximately normal. So that's important because I can use a z-table and do normal distributions as long as I have a sample size of 30 or greater. If the sample size is less than 30, then I have to do all this stuff to prove that it's normal so that I can use a z-table. But as long as your sample size is 30 or more, then the central limit theorem tells me that it's going to be approximately normal, and I don't have to worry about proving it. All right, so there's going to be two properties of these sampling distributions of means. The first one is the mean of the sampling distribution, which we're going to use the symbol mu like we have in the past, but this is going to be mu with a little sub x bar. And you'll see why in just a minute. It's going to be equal to the population mean. So we're going to say mu sub x bar is equal to mu. Okay, quick reminder, it's been a long time since we talked about this, but way back at the beginning of the year when we first started talking about stuff and I introduced these symbols to you, I know you don't remember because we don't revisit it, but this is mean, mu is mean, and so is x bar. Mu is mean of a population, and x bar is a mean of a sample. So if I was doing what I was just talking about a minute ago, I was going to do some sort of study of GPAs at Springtown High School. I could go down, and I'm sure that Miss Mayo could get something out of the computer for me, or Miss Kelly, one of the counselors. She could probably find the overall GPA at Springtown High School. I'm sure that Skyward would generate that. And that would be the population GPA, the mean GPA. Or I could take and that would be mu. If it was every student at Springtown, they added their GPA up and divided by how many students we have, the population GPA mean would be mu. Yeah. If I took samples of 50 students and got the mean of those 50 students, that would be x bar, because that's a sample. So you understand when we use the two different symbols. X bar is for a sample, mu is for a population. Then, for this distribution, we are taking multiple samples, so that's where, and taking the mean, and that's where this x bar comes in, and then we're going to find the mean of all those means. So it becomes the mean of the population of the samples. We're going to do one in a minute, and I think it'll start to make more sense. But that's why we're blending the two symbols together. Okay, y'all sort of okay so far? It's not complicated, I promise. It's just, I want you to understand the symbols so that when you see them, you're like, oh yeah, that's why. And then this is the standard deviation part of it. To calculate the standard deviation of a sampling distribution, which instead of just plain old sigma, we're going to do sigma with a sub x bar because it's coming from all these samples. You divide the population standard deviation, which is just sigma, by the square root of n. So it's going to look like this. And that's because we're making an adjustment for each one of the samples. Okay, so it seems like a lot at first, but I promise when we do this first sample, I think it'll make sense. Or it'll at least start to make sense. Okay, so the first thing we're going to do is we're going to look at a small population of numbers, 2, 4, 6, and 8. That is our population. So central limit theorem does not apply because my population is so small, I can't take a sample of 30 or more. That is my entire population right there. So this is the worst page turn ever. It wants me to list all of the possible samples of size 2, but I need them on the next page, and so I'm actually going to write them on the next page. So I'm going to write them up here. You can write them in both places if you want, but I'm going to write them up here. So if this is my, so here's my population. This is what we're saying. So I wrote all the numbers down earlier. So here's 2, 4, 6, and 8 all written on a piece of paper. I'm going to put them in a hat, and I'm going to draw out a number. It could be what? 2, 4, 6, or 8, right? My first number could be 2, it could be 4, it could be 6, and it could be 8. Now with replacement, that means I'm putting it back. And so when I go to draw another number, that number could be 2 the first time, or the second time. So I drew a 2 the first time and a 2 the second time. And right here I drew a 4 the first time and a 2 the second time. So I could draw a 2 the first time and then a 4, a 2 and a 6, or a 2 and an 8, right? I could draw a 4 and a 2, a 4 and a 4, a 4 and a 6, and a 4 and an 8. I could draw a 6 and a 2, a 6 and a 4, a 6 and a 6, or a 6 and an 8. Everybody understand where those are coming from? Okay. All right, so now we'll do what this actually says. To calculate the mean of each of the samples. So I'm just going to do it in my head because it's pretty easy to calculate the mean when all you have are 2 items. Add them together, divide by 2. 2 plus 2 is 4, divided by 2 is 2. 2 plus 4 is 6, divided by 2 is 3. 2 plus 6 is 8, divided by 2 is 4. 2 plus 8 is 10, divided by 2 is 5. 4 plus 2 is 6, divided by 2 is 3. 8 plus 8 is, 4 plus 4 is 8, divided by 2 is 4. All right. Each one of those those numbers that I wrote in green is an X bar. That's the mean of my first sample. That's the mean of my second sample. So these are all individual X bars. I am gonna just do this part of my calculator just because. I'm gonna enter all of my X bars into my calculator. 2, 3, 4, 5, 3, 4, 5, 6, 7. Okay, so there should be 16 numbers total. So I have 16 X bars. I am now going to find the mean of my X bars. Right here?
Yeah. Oh, you put all of those in the
Uh-huh. Do y'all understand what these are?
No.
Okay. I found, so do you understand what the 2, 8, the 2, 2, the 2, 4, the 2, 6, and do you understand what those are?
Yes.
Okay. I found the mean of them.
Okay.
2 plus 6 is 10, divided by 2 is 4. So the mean of this sample is 4. The mean of this sample is 3. Does that make sense? Okay. And now I am finding the mean of the means. So I'm finding the mean of my X bars. So does that make sense?
Yes.
So because there's 16 of them, I went ahead and just put them in the calculator. And now I'm going to find the mean by doing stat, arrow over to calc, do one variable stats. Now, if you've been using your calculator with a frequency list, we don't have a frequency list in right now, so clear that. So we're only finding the mean of list 1, and I'm going to calculate it. And the mean is 5. So that is the mean of the X bars is 5. Does that make sense why we are using that symbol? Because we just found the mean of a bunch of little means. So the mean of the mean. 5. All right, we good so far? It can be confusing if you're not like right on top of it, so I just want to make sure everybody's with me. We good? Okay, so now remember what my original population was. It was 2, 4, 6, and 8, just 4 little numbers. They want me to calculate the mean of that. So I don't have to put that in stat edit. I'm just going to add 2 plus 4 plus 6 plus 8. There's 4 of them. Divide by 4. And I get 4. The mean of my population, which is just mu, I'm sorry, it's 5. I did it backwards. There's only 4 numbers to divide and you get 5. Compare the two things. They're the same. Now in this case, they came out to be exactly the same. But if we were to do what I was talking about earlier, if I were to go downstairs and ask Miss Kelly, hey, what is Springtown High School's average GPA? And she gave me the average GPA of the population of Springtown High School. And then I took 15 samples of 50 and got their GPAs and then found the mean of their GPAs. It probably wouldn't be exactly the same, but it would be really, really, really close. Within like hundreds of a point, it would be that close. So because of that, we can always say that m sub x bar equals, that mu sub x bar equals mu. So we're gonna say that it always works out. It works out within decimals of each other. Does everybody understand what I mean? When I'm talking about it, like I don't mean mean, average mean. I mean, do you get it? We good? Okay. It's okay, it's okay.
That's me right now. That's my allergies.
Okay, so now they want us to actually graph the population, the distribution. So the first thing we're going to do is graph our population distribution. So our population was 2, 4, 6, and 8. Just because it's small and I got all this room down here, I'm going to make my bars a little wider. So I'm going to do 2, 4, 6, and 8. And let's see. So this is my population down here. And this will be my frequency on the side. And if I'm doing my actual population, there was 1, 2, so just so I don't have just one little bar, let's say that this is 1/4. So this would be, there was 1, 2, and there was 1, 4, and there was 1, 6, and there was 1, 8. Anybody remember what it's called when the distribution makes a rectangle? Y'all remember what kind of distribution that is? Uniform.
What do you mean there's 1, 2, 1, 4?
In my population,
Oh, okay.
there's 1, 2, 1, 4, 1, 6, and 1, 8. Now let's graph our sampling distribution. Now if you look at our sampling distribution, we're talking about the sampling of the means. And my means are all right up here. My means, I wrote them in green. So, all right. So first of all, I have to figure out what I'm going to put down across the side. I have more than 2, 4, 6, and 8. 2 is the smallest one I have. I do have a 2. But I also have a 3. So I'm going to start here again. 2, I have 3, 4, 5, 6, 7, and 8. 8's the highest number I have. And then I'm going to count, and these are going to be halves. So this is 1, 2, 3, 4, 5, 6. All right, how many times did 2 appear as a mean up there?
1.
Just 1. Okay, so just 1 of these.
Oh, no.
How many times did 3 appear?
3,
Uh-huh.
2.
Yeah, twice. How many times did 4 appear?
3.
symmetrical, it's bell-shaped, and the peak appears at what number? And 5 is what to us? What do we calculate 5 to be? Yep. That means it is normally distributed. Okay. Okay, so the two properties of the central limit theorem. All right. So the first property about central limit theorem is that as long as I'm drawing samples of 30 or more, the sampling distribution is approximately normal. And by approximately normal, we mean exactly what I just showed you. It's going to be bell-shaped, symmetrical, and the peak will be at the mean. That's what we mean by approximately normal.
I just wrote it, but I think it's something.
The other part of this is, if the population itself is approximately normally distributed, any sample size will be normal. So if I know that the population is normally distributed, then I don't have to worry about selecting a sample of 30 or greater. And sometimes in problems they'll tell you, from a population that's approximately normally distributed, and that's your indication that it's okay to use a sample size smaller than 30. Variance is just standard deviation squared. So in this case, because the error of the means has that standard deviation over square root of n, if you square the square root of n, it's just n. So and they'll call it the standard error of the means, or the standard deviation. All right, is it time? It's time, isn't it?
Yeah, but ain't no water.
All right, we'll do a little fast. We have 5 minutes. So. All right, so let's do one. I promise it. See, that was a whole lot of preparation, and when we do it, you're gonna be like, this is so much like we already just did. Okay, so how much is your cell phone bill? Cell phone bills for Ms. Hogan-Stats students have a mean of $87 and a standard deviation of 11. Suppose Ms. Hogan takes a random sample of 38 cell phone bills of her students, find the mean and standard error of the sampling distribution, that's standard deviation, of the sampling mean, and then sketch the distribution. All right.
Go back to
Yes, go. So my mean, my population mean, my mu is 87. Because it says right there, they have a mean of 87. And the standard deviation of the population is 11. Now, we just learned that if mu is 87, mu sub x bar is also 87.
That's always gonna happen.
That is
right?
always going to happen. But my standard deviation sub x bar, I have to do standard deviation divided by square root of n, and n in this case is 38. So I'm going to plug that into my calculator. And I get 1.78. So if I was going to sketch my distribution, my mean is still 87, but each standard deviation is going up only 1.78. So this would be 88.78, and this would be 85.22. Because I add 1.78 to get to this one, and then I add 1.78 again, and I get 90.56. Or I go for my mean and go down, so 87 minus 1.78, and then minus 1.78 again.